And as Anna mentioned, today I'm going to take you through how to do an approach to doing text classification with Spark. So I have a lot of material here. The agenda looks like this. And the assumption is that, I know Braden did a call last time with kind of more of the basics of Spark. So I'm going to quickly review that, but we're going to kind of dive more deeply quickly in this particular web conference. So I'll just do a quick overview of Spark, then I'll talk about, and we're going to focus in on Spark MLlib, which is Spark's machine learning library. Then we're going to talk about a specific use case, which is text classification using Spark MLlib. And then we'll kind of go over some machine learning concepts that will help you kind of understand what we're doing in this particular example. And depending on the time, we'll see how deep we can go on that. And then hopefully we'll spend maybe half the time on a demo where we'll walk through actually a use case of doing text classification on newsfeed documents and bring all of these concepts together. So just a quick little review of Apache Spark. So Apache Spark is a distributed computing framework that takes good advantage of memory, and it has a core set of APIs that help to manage and deploy applications this way. But on top of that, there are also several abstraction layers, and some of it we'll talk about in this session. One of them is a data frame API, which basically kind of gives a relational flavor to the data and the way that you can manipulate and use it. And then Spark has a number of different libraries for different purposes and capabilities. So you can do SQL on Spark. Spark has a streaming library to do streaming analytics. The one we're going to focus on here today is machine learning. And then there's also a graph processing library. These APIs can be accessed in a variety of different programming languages. Spark itself is written in Scala, so that is available to you. And then there are other programming languages like Java, Python, and R. We're going to use Scala in this particular example because some of the functionality that I want to exploit was only available in Scala at the point in time when I did this. And then Spark also, the other thing I want to mention is that Spark itself does not have a storage layer, and it depends upon other storage layers. And it can sit on top and use storage from virtually anything. In this particular example, we're not going to really worry about the storage. I'm only going to use a local storage because the point of this is more to get, to give you the machine learning concepts and specifically for this text analytics use case. And I don't know how to disable that, but it's a little annoying, but it keeps popping up. I'll just have to keep making it go away. So Spark has a number of abstractions. The original one that came with, originally with Spark is something called the Resilient Distributed Data Set, or RDD. This is basically a distributed collection of objects, all of the same type, across the cluster. A few things to note about RDDs is they're immutable, and that once you have data in an RDD and you operate an RDD, all the data is operated on in parallel. An enhancement to that came over time is this concept of data frames. Data frames are data organized into named columns. So conceptually, this is like, most of us are familiar with relational database, so it looked like a relational database table. And there are other programming languages who have this type of capability. Both R and Python have data frames, and it's very similar to that. So it makes it easier to work with the data, a little bit easier to understand. And the big thing kind of shown and depicted in the graphic below is because of the way the data frame is constructed, Spark is able to do optimizations on the data frame that it can't do in an RDD, where it can't really get inside. The RDD is a little bit more opaque to Spark. And because of that, regardless of now of what language that you use, you get similar performance, whether you were using data frames in Scala, Python, or any of the other various languages. For those of you who are not familiar with this whole notebook paradigm, and you'll see this in action because we're going to run the demo in a notebook. Um, we're going to be running this on IBM's Bluemix Spark as a service, and our Bluemix Spark as a service utilizes Jupyter notebooks. They're based upon IPython. Notebooks really became popular in Python. And what it allows you to do is to create cells that have code in it that you can interactively run. It also allows you to document within the notebook, so you can have text cells and things of that manner. You can bring in, media, videos, whatever you want to kind of, enhance the experience of a user using the notebook. But the big thing about it is it provides for like iterative analysis, so you can make changes and rerun cells. And so for data scientists, it's really nice. A really nice interface to work with. And it also allows you to kind of collaborate between users, and that you can have different people, they can kind of pick up and see what's going on in the notebook and add to it. All right, so that's the basic high-level, flyover of Apache Spark, and hopefully most of the people on this call are familiar with this. So now let's talk a little bit about Spark MLlib, the machine learning library. So again, Spark's machine learning library is called Spark MLlib, and what it does is it provides scalable machine learning on top of Spark, which is no surprise because Spark in itself is scalable, and Spark MLlib basically sits on top of all of those capabilities that already exist in the core Spark product. It comes with a number of learning algorithms, so things like classification. You can think of that like I have transactions. Are they fraud or non-fraud? Regression. If I have if I'm trying to predict housing prices and I have a number of characteristics of that house, how many bedrooms, square foot, on and on and on. Can I, given a set and I train it on a set of examples, can I predict a house that a price of a house that it should be listed at? Clustering, taking data, for instance, market basket of analysis, take a set of products and see which ones are typically bought together. That would be example. And collaborative filtering is ubiquitous these days, used for like recommendation engines. So every time you go on any kind of website and you get recommendations for buying a different product, or maybe here's another movie you want to look like, that's typically collaborative filtering. So Spark machine learning itself has a number of lower level operational primitives. We'll use some of those, but what we really want to focus on in this particular example is some of the newer higher level APIs that are available in Spark MLlib and how you use them. And we'll see again examples of that as we go through the demos. So typical examples in an ML pipeline is what this is an example of, like can you hear me?
I can hear you fine now.
Okay, I'm sorry. I don't know what happened. I got dropped. Sorry about that. So the way that a pipeline works is, in this particular example, we're looking at detecting spam email. So we'll take the email and we'll extract features from it. So in this particular case, you can think of it, one example would be to tokenize it and pull out words. And then once you have that, you want to create a model. And again, in this particular case, we're trying to classify it as spam or not spam. So we create a model and we would train a model that would be able to make that distinction. And then the other piece that you do is you want to do model evaluation. So what would happen is we would look at, how do we best fit the model? How do we pick the specific model parameters that would allow us to, make the best predictions? And we'll see examples of this as we go through the rest of the presentation. All right, so now we're going to move in specifically, how do I do text classification with Spark? So one concept that I wanted to just review before we go any further, this has nothing to do with Spark, but machine learning in general has two broad categories of the type of learning that you could do. There are others, but we can kind of focus on these for now. The first is supervised machine learning. In supervised machine learning, you train a model on a predefined set of training examples. Basically what you do is you give the model the right answers and you let it learn from that, and then the idea is that it can make predictions on data that it has not seen. The other category of machine learning is called unsupervised machine learning. In unsupervised machine learning, you're not giving the data labels and you're not necessarily looking to make predictions. What you're trying to do is look for patterns within the data. In this particular example, we're going to be looking at and using supervised machine learning data, and that we're going to take a set of documents that have a label. We already know how they're categorized. We're going to learn off of that, and then we're going to go forward and then predict for documents that the model has not seen. So what we're going to use as an algorithm to do this is called classification. So classification aims to divide things into categories. Like I mentioned the example before, fraud or not fraud. In this particular case, the category is going to be a topic. You can do binary classification, which means I'm just looking at two categories, or you could do multiple classification, meaning that you're going to look and try to categorize things into multiple categories. Logistic regression is very popular for doing binary classification. Logistic regression can be generalized to do multi-class classification. Unfortunately, in Spark machine learning and the libraries available today, it doesn't natively support that. There are ways to get around that. There's ways where you could take one category and then look at that and compare it to everything else, and then keep switching the category and then aggregating the results. And that is possible, but a little bit more of a complication and not something that I wanted to get into in this particular session. But the ideas that I will show you here would be extensible to be able to do that kind of analysis. So let's go over some Spark machine learning terminology. So basically a pipeline is the development of a workflow. What you're able to do is chain together stages, and these stages can be transformers, and a transformer is an algorithm that can transform a data frame into another data frame. And that could be for several reasons which we could discuss, but it may be you want to do some kind of feature engineering and you need to prep the data and get it in a certain format. Also keep in mind the data frames are immutable, so you're not going to actually change the data. What you're going to do is create a new data frame that has an additional column with the transform data that you're doing with the transformation. The other thing is an estimator. That allows you to fit a data frame and basically produce a transformer. And in this case, the transformer is something that would make a prediction. And in our case, the estimator is going to be logistic regression. We already talked about a pipeline. And then each of the stages have the ability to set parameters, which we'll see in a little bit more detail. It basically tell how the stage will actually work, and you get to specify that in terms of not only what are the inputs and outputs to it, but any characteristics that may, parameters that may enable it to act differently. So transformers are an abstraction, and we have feature transformers and learned models. So a feature transformer is kind of what I talked about before, and in our particular example with doing text classification, one feature transformer would take the corpus of one text document, and then it would tokenize it, and then create a new column in a data frame that had the data tokenized into words. So that would be one example of it. An example of using it on a learned model would be that I could make predictions using the learned model, and I would get a new column in my data frame where were the actual predictions. So again, that's an example of a transformer, and it could be something that you're doing like for feature engineering, or when you're actually making predictions from a model. So here are some feature transformers that we're going to, and this is not a comprehensive list, and these are the ones that are probably most prevalent for text classification. So tokenization, and I kind of mentioned this before, it's the process of taking, text in the sentence, paragraph, whatever it may be, and breaking it into individual terms, words, tokenizing it. A second one would be stop word removers, and in this particular case, the idea behind stop words, and let me define stop words first. Stop words are words that are like common, so they don't really add a lot to the categorization. So, for instance, you can think of stop words as things like and, I mean, they exist in every corpus of document, and they're not really going to add in terms of the classification. So typically you want to remove those to kind of limit the number of features that you're analyzing to not only optimize the categorization, but also to actually help from overfitting the data if you have too many features. So a few other transformers. One is called inverse document frequency. So in inverse document frequency, actually term frequency, inverse document frequency, there are two parts. So the first part is called hashing TF. And in hashing TF, we're basically going to hash the words, in this case, to a fixed number of hashed values. So what this allows us to do is to, again, limit the number of features that we're going to analyze. And then the second one is called inverse document frequency. What this does is that, when you're doing this kind of analysis, you really don't want to focus on words that exist in all of the documents. If a word exists in every document, it really provides no differentiation. So what IDF does is it downweights those type of words in the analysis, and it will bring to the forefront other words that are more distinctive and only occur in a lesser frequency in certain documents. So estimators are the things that you implement a model with, and that you can learn a model with a fit method. So an example is we're going to be using logistic regression as our estimator. That's what we're doing to do this binary classification, and we're going to learn a logistic regression model that we then will use to make predictions. So we talked about pipelines a little bit, but again, just to review, it is a sequence of stages where each stage is either a transformer or estimator. Those are the two, the basic two stage types that we already talked about. And when you define a stage, the stages are run in order, and the input data frame that you pass to the stage is transformed as it passes through the stage elements, the stage components. And transformer stage have a method called on it to transform it, and then the estimator stage are fitted with the data that is flowing through it. So as an example, in the workflow, and ours is going to be a little bit more complicated than this, but we're going to split the documents into text words in our pipeline. Then we're going to convert each of the documents into a numerical feature vector. That's using the hashing TF that we just described a minute ago. And then we're going to learn a predictive model using these feature vectors and labels, which we'll talk about in a little bit more detail when we get into the demo. But what you got to do is to construct a pipeline that has these various features, transformers and estimators, and the pipeline will run them in a particular order so that you can train a model, and then as we'll also see, you will be able to use it to best fit a model later on. So here's what it looks like from a text classification use case point of view. So in this particular case, we're training a model. So we have a model. We have raw data coming in on the left side, and we're tokenizing it. We're going to do a few other things, but just simplification. We're going to tokenize it into words, and then we're going to use hashing TF to create feature vectors, and we're going to limit the number of feature vectors to make it easier to get a better model. And the result of this, and the estimator we're using, is logistic regression for classification, and the output that we get out of this is a logistic regression model. So we create our pipeline, and the way that you enable all that, and you see this in the demo, is there's a method called fit, and you're going to fit on the particular data that you're trying to learn the model with. And in most cases, it'll be your training data. So once you now have a learned model, what you can use that learned model to do is make predictions. So again, after the pipeline fit method runs, it produces a pipeline model, which is the transformer, and now that transformer can transform data frames, and the way it transforms data frames is by making a prediction and adding an additional, as an example, an additional column to the data frame that has the predicted values. And that's kind of depicted here below. So I fitted my pipeline earlier on the last slide. Now I can actually make predictions against that pipeline, as an example, using the transform method, and then all of the same steps will occur, but this time now I already have my logistic regression model that I learned in the previous step, and it will be used in this case to make predictions on my data. And in our case, with the text classification of documents, the prediction will be whether it's in one category or another. So there are a number of parameters when you're working with machine learning. You can think of these, they're called hyperparameters, and they're kind of like knobs that you turn in order to make the model work better. And you can make educated guesses, and there's some science behind it, but typically what's going to happen in the machine learning workflow is, and we'll see how we do this in the demo, is you're going to pick some values and empirically test those different values and see which ones give you the best result. So you're going to make educated guesses, but then you're going to use and specifically use the pipeline that we developed to test out various combinations of these hyperparameters to come up with a best fit model. And again, we'll see that in the demo. And the way that you do this best fitting in Spark ML is there's a class called cross-validation. And cross-validation, and this whole idea of doing best model selection is important, right? Because you don't know what these hyperparameters should be. And using pipelines and this cross-validation class, which we'll see in the demo, it'll allow you to iterate through the pipeline with different values of the hyperparameters to determine what is the best set of parameters. And kind of shown in the diagram at the bottom, because there are different ends of the spectrum, right? You could be underfitting your model, kind of shown, and this is not for a classification problem, but you kind of get the point. It doesn't really fit the data, right? You would probably want to see something a little bit more quadratic there. The other end of the spectrum is on the right-hand side, where it's it's too closely fit to the data. The problem with this is if I made predictions on the training data that I used to train the model, it would do very well. the issue is that it doesn't generalize. So if I then went ahead and gave it data that it hadn't seen before, it probably would not do a very good job at it. So both of these on the left-hand and the right-hand side are not optimal for different reasons, but what we want is kind of something in the middle, which is just the right fit. And this is what we're going to use cross-validation for in the demo, to try to uncover what parameters help us to get to that best fit. All right, so before we jump into the demo, what I wanted to do is just review a few other machine learning concepts that will, I think you'll need some of this information to kind of understand a little bit better what's going on as we walk through the code. So we already talked about the fact that we're using supervised machine learning. This is a kind of, and we're not going to get into the technical details, so don't worry about the math here. This is a picture of a logistic regression. If any of you have done like this kind of stuff in college, this is the famous sigmoid curve. But basically, what we're doing is we're trying to classify, and we're using this sigmoid curve basically to predict a label, whether it's 0 or 1. Whereas what's in blue would be kind of more of a linear regression model, where we were trying to, on a linear straight line, trying to figure out where the values fall. In this particular case, we use this sigmoid function because we want to push things towards one label or another. Is it fraud or is it not fraud? And this is what enables us to do it. So there's just a little bit of details behind a logistic regression. You don't really need to understand this, except for the fact that logistic regression, because of this, is going to enable us to do binary classification. So another thing you need to think about in binary classification with logistic regression is, okay, where do I draw the point, right? So what that curve that I showed you on the previous slide is on the vertical axis is the class probability, right? It's going to make a determination. What is the probability that these set of features fall within this category? And where do I draw the line? So by default, it's 0.5. So if it has a greater than 0.5 probability, we're going to give it a label of 1. And whatever you define 1 to be, maybe 1 in this case means it's fraud, and that's the way it would be classified. But with logistic regression, you do get the probabilities. But you may want to alter this, right? Depending upon what your use case is. Again, if I'm trying to predict fraud versus not fraud, or I'm giving it features associated with tumors in a patient, and I'm trying to predict cancer versus non-cancer, I may want to, think about where my threshold is, because, the implications of having, too many false positives or too many false negatives, could be very serious. So you would need to kind of think about that a little bit. But in this case, I just wanted to show you what it is, but we're going to just stick with the default of 0.5. So what you do is you have all of these. So if you run a model, and you can kind of look at the results, right? So I can see how many we just talked about, like false positives and false negatives, but there are also true positives and true negative. And when you put these all together, you get what's called a confusion matrix that kind of shows you this graphically in a table. And so this would be actually a good thing to use when we want to evaluate how good a model is. The problem is it's not like a single number, right? So it's difficult to just like compare against and say, well, how good am I? Well, I'd have to look at all these different, all these different characteristics. So one of the things that is done, there is we're not going to go deep into it, but I wanted you to know what it is because we're going to use this. It's called receiver operator characteristics, or ROC curve, or you may hear it called ROC curve. This is very well known, in machine learning and statistics. And basically what it is a graphical plot that shows the performance of a binary classifier system, in this case using logistic regression, as its threshold value is varied. And you get these kind of curves, and it's basically plotting true positives versus false positives. And this line here, the straight line basically means it's no better than a guess, right? You know, if I just flipped a coin, I would get these. But these curves up here are better and better. And so the closer it is that this curve hugs both of the side, the left-hand side and top axis, the better. So the metric that we end up going to use is something called area under the curve, because we're going to look at the area under this curve, and the more that these lines are pushed up into this corner, the more area there would be. So for this line, it's 0.5. So if you get a metric of area under the ROC curve of 0.5, it's just like flipping the coin, but you want something that's potentially closer to 1. So this is, again, the metric that we're going to use as we go through the demo, and I wanted you to just see what that was. One of the hyperparameters I just want to talk about quickly, and we talked about overfitting and underfitting a little while ago. This one's more kind of showing a picture using classification, so something like that you would do with a logistic regression. So we have a set of points here, and they're labeled, and the color represents the label. And we're trying to come up with a model. We're using a linear model in this case, so with in 2 dimensions. We're trying to show the line that best fits this. And this particular one, there may be like some better lines that may be angled more like that, that would do a better job. So we would call this one probably underfit. And as kind of the example I gave before, this one right here is probably overfit. It would do a good job, so on this data that I trained against, of making predictions on that, but it wouldn't generalize well. If I gave it a new set of data that it wasn't trained against, it probably wouldn't give very, very good results. So there is a parameter, don't worry about the math here. This is just the cost function, the math behind the scenes for logistic regression. And this term at the end is typically called lambda. And what it is basically a penalty. It's called a regularization parameter. And all I want you to come away with this is it penalizes having a lot of complexity in your model. And that's what this kind of theta squared means. It's the parameters of your model. And so what this basically represents is a trade-off between getting the best model but not having it very complex. And so the reason I'm showing you this is just so you can see a little bit of the intuition behind a regularization parameter, and that is one of the hyperparameters that we will look at when we go through the demo. So that's all the backup material that we need. Just before we actually look at Spark itself, I just wanted to set up the demo in a little bit of detail, because I know sometimes as you go through these, it's a little easy to get lost behind the trees. So the demo scenario that we're going to be using here, we're going to do text classification against a 20 newsgroup text classification data set. Again, obviously using Spark machine learning, and we're going to classify into 2 categories, binary classification. Specifically, in this example, we're going to look at whether the documents are computer-related or non-computer related. So the newsgroup data set consists of approximately 20,000 newsgroup documents. They're split pretty evenly across 20 different newsgroups according to topic, and a lot of people use these, for these kind of text applications and trying out machine learning techniques. In this particular demo, we're going to use a subset of this. So rather than just to make it simpler and faster to run, we're going to use 2,000 articles rather than 20,000, but the same 20 news groups, so 10 articles per news group. And I just wanted to include here, because I did use their data set, this is an acknowledgement of where I got the data set from. So this is what the topics look like. So you can kind of see the first level qualifier is higher level qualifier is the computer. Does it have to do with recreation? Does it have to do with science? And then the second part of it gives a little bit more detail. This is showing it graphically, and what we're going to be focusing in on here is try to identify ones that fall within this computer branch. Is the document related to computers or not? So the way that this physically gets instantiated in the document, the data that we pull down, is they're in directories. So each of the 20 news groups are arranged by topic in a directory, and there are 20 directories, one per topic, and then each of the directories has 100 files in it. So one file represents one document. So if I opened one file, it would have all the text associated with one of these documents. And then the subdirectory name represents the topic. So these, and we'll see how we extract this out, but this is the subdirectory name. And then you could see, I could pull out from here that this was computer related because it has, it's in a subdirectory with the word COMP in it. So the demo flow looks like this. That the place that I referenced earlier, they have it's a download site where you can download this mini news groups. This is the 2,000 rather than the 20,000. It's in a tar GZ format, so you can download the tarball. We'll do that in the notebook. We can explode it using, just using tar to explode it. And then we're going to read the news groups into an RDD using a method in Spark called whole text files. And what whole text files returns is basically a RDD pair or a tuple that has the file path and the content. And we'll see how to deal with that. And we're going to have to extract information out of it, because out of that pair, we're going to extract the file path, and then we're going to extract the content, and then we're going to put them in the data frame and use we're going to use the data from the from the file path to actually label our data, because we saw it had whether it was comp or non-comp in it. And so we're going to again take data that has the word comp in it and label it as a this has a mistake. It should have been a 1. And we're going to label that as a 1, and then those that are non-computer related we will label as a 0. Logistic regression requires that the label be numeric and that actually be of type double, and you'll see we'll do that in the notebook. And then what we're going to do is we're going to split the data into training and test data sets, and then we're going to configure the pipeline we talked about with all those transformers, tokenize, stop words, hash it, do that inverse document frequency to downweight commonly used words across all the documents. We're using logistic regression. We're going to fit the pipeline to the data training models to get a learned model, and then we're going to show predictions on the test data set. And then we're going to go ahead and tune the pipeline using as an evaluator that area under the rock curve that I showed you, and generate hyperparameters, combinations that we will iterate through to find the best, basically to find the best fit model. And then once we have that, we'll make improvements. We'll make predictions based upon this improved model. So I'm going to flip over right now to the Spark notebook. Again, so this is a Jupyter Spark notebook running on IBM's Bluemix platform. And what I want to do is kind of just step you through some of the stuff that we talked about. So first, what we're doing here is this is just operating system stuff, and the point of this is not to go through the syntax. It's basically to give you the ideas. We just, in this limited time, we don't have time to do that. But I want to tell you what I'm doing and why I'm doing it, and how it matches up to the concepts that we already spoke about. So what I'm doing here is basically just downloading the data set. So we're using wget to pull that off of a website, that tar.gz file, and you can see here it all is right there. And then what we're going to do is explode the tarball. So we're just going to do a tar xvf, and here are the results. I suppressed it. I didn't use v because it would have been a whole long list, so I just suppressed it. But you can see the output was 0, which means there was no error. And then if we go back and now just do an ls minus l and see, we're loading this just by the way I mentioned before, just on local storage. Just as an example, this is probably not something that you would do in production, but I'm trying to get a point more of the, what are the thoughts behind doing this, and how do you do it as opposed to making this necessarily production ready. So you can see there are the 20 directories, and each one of those the directory names have the topics in them. So we downloaded the data, and now we're kind of ready to go. I just verified here that we have a Spark context up and running and a SQL context. So you can see we're running Spark 1.6, and that we do have a SQL context that we can use. Then what I do go ahead here is just just import all the Spark libraries that we need. And you can see some of the stuff we already talked about. We need hashing TF, we need stop words, we need IDF, we need tokenizer, cross-validator to the hyperparameter tuning and stuff like that. So I'm just pulling down all at once all of the various Spark libraries that I need. Then what we do is we go ahead and read it in using the whole text file method. And as we kind of talked about earlier, what you get from this is a RDD pair or a tuple with the file name and then the contents of the file. And if I do after I download it, if I do a count on it, you can see I did indeed pull down 2,000 documents. And if I want to then go ahead and kind of look at an example of the contents of what I pulled down, you can see it is a tuple here. The first element of the tuple is the file name, which is all the way up to here, and then comma, and then the second element is the actual data, and then that's basically the rest of what goes on here. And this is what we'll be using to train and to make predictions on data going forward. So what I'm doing here, and this is just again the method I'm using is this came in predefined directories, and so I'm pulling the information out of the directory to be able to create a data frame that I can then feed in the pipeline and do the machine learning that we talked about. So what I'm doing right here is just stripping out the file name from the content from that tuple that we had. So I only want the file name, and so if I look at that, I was successfully able to pull out the file names. And then if I want to pull out the text, this is using a construct in Scala called case classes. Not really going to talk about it any further, but it's a way to do pattern matching and pull out what you need. So here I'm pulling out the text, and I'm pulling out the text here from that tuple. And then if I go ahead and then I'm taking a sample of it, just looking at it, I can see this is the text of one of the newsfeed documents that we're looking at, just a random sample. When we train the model, we're going to be using everything. And then what I also wanted to do was pull out from the what I wanted to pull out from that tuple was the ID, which was if you remember, that was the file name. It went file path and then ID, and just kind of use that as a way of identifying each one of the text documents. And then the other thing I wanted to do, because we want to use this as a label, that I want to pull out the file path, the information, the topic information out of the file path. And this is the syntax that I used here to do all of that. And you can see these are the resulting topics that I came back with. And then what we do is I want to stuff this all in a data frame, because one of the good things about MLlib is it works directly on data frames, so it makes it easy to work with. I needed to go through all this manipulation because that would not have been so easy to do in data frames. So you can mix and match, use RDDs, data frames, whatever makes sense. But here we are right now, is I now have a data frame that has the data that I need to create a pipeline, create a model, and then best fit it. So I have the ID of the document, I have the text that's in that document, and then I have the topic of that document, because this is what we're going to be classifying with. And then if I go and just look at the counts, I can verify that it seems like I did everything okay, because I have 20 topics, categories, and there were 100 in each one, so that's the whole 2,000 documents are accounted for. And then we can look at which ones, and I just want to show you the way I'm finding which ones are computer related. I'm just like SQL, there's the data frame API in Spark has a like method, so I can say like comp and see which ones have computer in it, and you can see that it did, when I run that command, it did pull the ones that have comp in it. So now this was all kind of like pre-processing, right? This was using the data in a way and getting it set up the way I wanted to be able to use to train my model. So now we're going to move into training the model. And what we need to do here is, first of all, we're going to create a label. So the label, again, was pulled from this, whether this topic right here contained the word comp. So here we're just looking at the topic and saying, does it have comp in it? And if it does, it will return this operation right here will return a 1, and if it doesn't, it will return a 0. And then I need to, and this is because logistic regression requires numeric labels that can't work with text labels, and it also requires for them to be of type double. So I have to cast that result as a double. And then if we look at kind of the resulting data frame after all we did that, now I think we have, it can show you that we have what we need. So this is kind of like what we had up above. We have the ID, text, and topic, but now we converted the topic to a label. Again, this was part of the transformations that we talked about earlier. So where they're non-computer related, the label is 0, and then cases where I do have computer related topics, the label is 1. And here I just pulled ones that were all computer related, and you can see the results were all 1. So now we have a data frame in a format that we can now use to do the machine learning and to actually train a model with. So the next thing that we want to do is we want to split the data into training and test data sets, because we want to have a set of data that we're going to train and learn a model against, but then we want to evaluate and test the model based upon data that the model was not trained against. And that's for reasons like we talked about before. This way we can see if there's overfitting, if the model didn't generalize well. It typically won't work as well against the test data, but it probably will always work well against the training data, because that's what you use to create the model. So here what we're doing is we're doing a random split and basically breaking the data down into a 90-10 split, and 90% of the data being training and 10% being test. And then after I did that, I just counted the number of rows that were in each one, or elements are in each one, and you can see we started off with 2,000, and now we have 1,700 change for training and 233 for count, and it broke it roughly in a 90-10 split. So we have the data, and now we can go ahead and configure our pipeline. So we talked about all those transformers when we went over the slides, and here's the way it works. We're basically going to call these classes, so like for tokenizer and stop word remover, and the hashing to hash the data values, to do the inverse document frequency, and then logistic regression, which is the estimator that we're using to actually make the classification. The thing I want to point out here is the way when you string these together, the way that it works is basically you want to have an input column, and text is already defined. That was in my data set up above that we already looked at. But then I can also string it together and say, okay, here's when I do that tokenization, I'm going to create an output column and a new data frame that I transformed with a column called words. And then what I'm going to do is in the next stage, I'm going to take the words, and then I'm going to operate on them and take out all the stop words, and then I'm going to call that output column filtered. And then I'm going to take the filtered, and I'm going to input that into the hashing TF, and then I'm going to call the output of that raw feature. So this is basically the way you string it together, by calling them in order, by being the initial input being one from the data frame, and then keep tying the columns together in this way so that one feeds the next. The other thing that's also stuck in here is there are some parameters, so you can see they're done with set methods. We don't have time to really go over these, but things like, what do I care whether when I'm doing the stop word remover, do I want case sensitive, or does it exactly have to match, those kind of things. But parameters that are associated with the particular pipeline element. And then what you do in this line here is you get to pull all the pipeline elements together by creating an array with all of these pipeline elements that I just defined up here above, and then using a set stages method to create the pipeline. And now I have a pipeline. And then there are ways to go back and look at the what the values that are in the parameters. Some of them you may have set, some of them may be default. Like I think in this case right here, I just wanted to show you that the if I look at the get the features column, because in logistic regression I didn't set it, so it assumed that it was the logistic regression features column is called features. That's the default. So I either need to set it, or I need to make sure the stage before it is outputting something called features. So that's just what I wanted to show you there. And then there's an explain parameter method. We're not going to have time to look at this in detail, but it'll kind of go through and show you all the parameters, what they mean, what the defaults are, and stuff like that. And then there's a method we talked about before, the stop words. It comes with Spark ML comes with its own list of stop words, so I can look at what those are by using this get stop word method, and you can see they're all listed here. If you wanted to provide your own list of stop words, you're able to do that, and either to supplement or replace what's the stop words that are here. So now we have a pipeline, and we can go ahead and fit it to our we want to fit it to our training data to create a pipeline model. So that's all that we're doing here. So now model is actually a pipeline model based upon our pipeline. And now we can use that model by calling, because a fitted model is a transformer, we can call transform on it. And this time we want to transform the test data, not the training data, because we trained on the test. We want to see how well it did on data that it did not see. So we're going to train on the testing data. And then I can go ahead and then look at what the results of that are. And you can see now I have again, I have like before, a prediction column, all my data, the ID, the topic, and the label. But what it did when I actually transformed using the model, it gave me added new columns. It transformed it, adding a prediction column and a probability. So logistic regression not only puts things in the classes, but it tells you the probability of the class. But let's focus on these, the predictions. So you can see that it got some right, but it actually also did get some wrong, where it had a predicted value here of 0, but the answer was 1. So that it's not in this, at least to this point, it's not perfect. And then you can actually show the whole. If I look at the whole data frame, now I can see exactly what I did here on the whole pipeline. So here was my ID, here was the text data that I had, here was the topic and the label. You already saw all that. But now here are the outputs of the different stages. So I have the words where I tokenize. I have it filtered where I remove stop words. I have the hashing TF where I created feature vectors and I limited it to 1,000 features to eliminate overfitting. And then I did other things like the inverse document frequency by down weighting the features, and then I get the probabilities and the predictions back. So up to this point, we've created a model, we created a pipeline, we trained it, and then the final thing we're going to do is just evaluate it and look at what are the hyperparameters that could best make the model potentially better. And so there's an evaluator class for binary classification called binary classification evaluator. We're going to tell the metric that we're going to use to make this evaluation is area under the ROC curve for reasons that we discussed earlier. And then if I go ahead and use that to evaluate the results that I got above, I get an area under the ROC curve of 8.6. So pretty good, right? We said 0.5 was like flipping coins. 0.86 is much closer to 1. But let's try different hyperparameters and different combinations of that. And what you use is something called a parameter grid. So what a parameter grid is, you get to define a grid of different parameters. So in this case, the parameters that are associated with each of the stages, I can specify what that is, and then I can create an array of values. So for this particular parameter called hashing TF num features, I'm going to look at 3 values: 1,000, 10,000, 100,000. Same for this one down here. And then when I create this grid and these actually get run, they'll be run in all combinations. So because I have 3 and 3, I'm actually going to run this nine times, or 9 different combinations and see which one out of those combinations are the best. And so that's what we're doing here, is just using a cross evaluator with that parameter grid, and we're defining it there. And then here we're actually running the model, so we're fitting on that cross evaluation model back using the trading data set. We could have split out a separate cross evaluator data set for this purposes, but all I want to show you the result of it now is the area under the ROC curve was 0.98. So we made significant improvements with the different combination of hyperparameters, and I just calculated what the improvement was, and it was 12.7%. And then once we have a better model, we can go ahead and then make predictions against that better model, just like we did before. But now it has the the optimized selection of hyperparameters because we did that cross validation. So just to kind of wrap this up, so what we saw here is, we looked at a specific use case for text classification, and allowed us to classify text documents into a fixed number of predefined categories. In this case, we only looked at binary classification, so whether the document was computer or non-computer related. But obviously, this has a lot of applications. We briefly show in the slides, spam, detecting spam email, and this case, classifying newsfeed contents, and examples can go on and on. So this particular example, showed how to do and put together a machine learning pipeline for this purpose, the text classification. But a lot of the concepts that I showed you here are really applicable to different, it didn't really necessarily have to be the text classification. You would use different transformers. We were using HashNTF, tokenizer, IDF, stop word remover, all of those kind of things. You would probably use different transformers in a different application. But you kind of see the idea of how the pipeline comes together, how you use it, and then how you best fit with it. And then we saw that MLlib had a high set, this set of high-level APIs that allowed you to construct the machine learning workflow. And again, the major benefit out of that is now I have this consistent workflow that I can use to both train a model and then to cross-validate and select the best set of hyperparameters, rather than having to do each stage individually, and it's prone to errors and that kind of thing. And again, in the pipeline, which is the thing that facilitates this workflow, the stages in there are run in a specific order as you go through, and we saw that how we chained a one to the other from the output column of one to the input column of another. So I know that was a lot of material. We can share with you obviously the slides, and if people are interested, we can share the Spark notebook so you could try to run through the code live yourself. So I hope this was informative. Again, I know it was a lot of information, but wanted to pass all of that along and then give it to you so that you maybe could review it and look at it in more detail on your own time.
Right.
So Anna, that was all I had for today.
That it would be great if you can answer, which is, what is the advantage of using Spark ML versus using SAS or R?
All right, so I'll answer the R one first. I mean, R is a programming language. So one of the things with if you just look at like straight R can only run on a single computer, so it's not scalable. So if you have a small problem, just doing it in R may be appropriate. If you have a larger problem where it's going to have to be distributed across multiple computers, then you need Spark. But as I showed in one of the, if I can get back up there, in one of the earlier slides, R is one of the languages that Spark supports. So we don't have to differentiate them. You can use R, and you can use your familiar R tools like RStudio to be able to get and use Spark as an execution engine, but programming in R. But the problem with just standard R is that it only can run on a single machine, so it doesn't provide the scalability that Spark does.
Okay, and the next thing that people wanted to know is whether we would share the slides and the notebook, which you already said we will. So I will make
Yes.
sure that everyone gets a copy of them. Okay, so with that, thank you so much, Rick, for your wonderful presentation, and thank you everyone for joining us. And if you want to stay informed and be invited to other webinars or meetups or any type of learning opportunities, please make sure you sign up at the ibm.biz-datagurus URL. Thank you.
Thank you.